Welcome to G Fun Facts Online. Today we are diving deep into a phenomenon that essentially breaks one of the most fundamental rules of our universe. We are talking about a system that defies the arrow of time, refuses to forget its past, and has forced physicists to rewrite the textbooks of thermodynamics. We are talking about the integrable gas. To understand why this state of matter is so revolutionary, we have to start with the concept of thermalization. In the macroscopic world we inhabit, the arrow of time seems absolute and irreversible. If you leave a hot cup of coffee on a table, it cools down until it matches the room's temperature. It never spontaneously heats up. If you drop a bead of ink into a glass of water, it spreads until the liquid is a uniform pale blue. It never gathers back into a droplet. These are manifestations of thermalization, the universal drive of nature toward equilibrium. This drive is the bedrock of statistical mechanics. The core idea is that given enough time, energy distributes itself continuously among all available particles. Crucially, the detailed history of the system is erased. Once that coffee is at room temperature, you cannot look at it and tell me how hot it was an hour ago. The information is lost, leaving only a few macroscopic variables like temperature and pressure to describe the system. This erasure of memory is technically called ergodicity. An ergodic system explores all possible microstates allowed by its energy. It does not matter how you started the experiment. The destination is always the same: thermal equilibrium. For decades, this was considered the inevitable fate of all complex many-body systems. But in the ultra-cold, ultra-isolated quantum realm, this rule is not absolute. Physicists have discovered a class of systems known as integrable gases that refuse to forget, like a pendulum that swings forever in a vacuum, or a hall of mirrors where images never fade. These quantum systems defy the chaos of thermalization. They bounce, collide, and interact billions of times, yet they remain locked in a perpetually non-thermal state, remembering their initial conditions for eternity. This brings us to the first major breakthrough in this field, the quantum Newton's cradle. You have likely seen a classical Newton's cradle on an executive's desk. It is that row of steel balls suspended by wires. You pull one back, release it, it strikes the line, and a single ball pops off the other end. Ideally, this motion repeats forever. In reality, sound, friction, and imperfect alignment eventually cause the balls to jiggle randomly, and the organized motion dies out into a thermal shudder. That is entropy winning. But in 2006, David Weiss and his team at Penn State University asked a question: what if we built a Newton's cradle out of atoms? They built a quantum version, using rubidium-87 atoms. Now, you cannot hang atoms on wires, so they trapped these atoms using tubes of intense laser light, creating a one-dimensional waveguide. This 1D aspect is crucial, and we will come back to that. They cooled these atoms to near absolute zero, creating a Bose-Einstein condensate, a state of matter where atoms march in lockstep. Then, using laser pulses, they split the cloud into two halves and kicked them toward each other, making them collide in the center of the trap. In a normal three-dimensional gas like the air in your room, these colliding clouds would act like billiard balls. They would smash into each other, scatter in all directions, and almost instantly turn into a stationary, hot ball of gas. The kinetic energy of the collision would become random heat. Thermalization would be immediate. But in Weiss one-dimensional tubes, something magical happened. The clouds passed through each other, oscillated to the edges of the trap, turned around, and collided again, and again, and again. They observed these atoms colliding thousands of times. Yet the momentum distribution did not relax to a Gaussian thermal shape. The atoms refused to thermalize. They retained the memory of their initial kick almost perfectly. The system was behaving not like a chaotic gas, but like a ghostly fluid that could flow through itself without ever mixing. This was the experimental realization of an integrable gas. So why does this happen? The secret lies in the geometry. The theoretical underpinnings come from a model proposed back in 1963 by Elliott Lieb and Lieb-Liniger. It describes bosons moving in one dimension with point-like contact interactions. In our familiar 3D world, particles can collide at glancing angles. If two balls hit each other slightly off-center, they trade momentum in continuous, complex ways. This redistribution is what leads to chaos and thermalization. But in one dimension, the geometry is strict. It is like a single-lane tunnel. If two identical point particles collide in 1D, they cannot go around each other. If they bounce elastically, they simply swap momenta. Imagine two identical balls on a line, one moving right at speed v, the other left at speed negative v. After an elastic collision, the one moving right is now moving left at negative v, and the one moving left is now moving right at positive v. Since the particles are identical quantum mechanically, you cannot tell the difference between them bouncing off each other or simply passing through each other as if the other ghost wasn't there. This simple property has profound consequences. It implies that the set of momenta in the system is strictly conserved. In a normal gas, only total energy and total momentum are conserved. In the Lieb-Liniger gas, the individual momentum of every single constituent quasi-particle is a conserved quantity. If you have a gas of 1 million particles, you have 1 million conserved quantities. These conservation laws act as straitjackets. They prevent the system from wandering through phase space to find thermal equilibrium. The system is what we call integrable. To solve the mathematics of such a system, physicists use a tool called the Bethe Ansatz, named after Hans Bethe. It is a specific guess for the wave function that assumes particles scatter only in pairs. Even if 3 particles meet at the exact same spot at the same time, the mathematics allows us to treat the event as a sequence of 2 particle collisions. Because of this factorization, the complex, chaotic, multi-particle entanglements that usually drive thermalization never form. The particles effectively rearrange their phases, but keep their speeds or rapidities. This is why the quantum Newton's cradle does not stop. The atoms are playing a game of quantum leapfrog, constantly swapping identities but never losing their collective energy profile. This discovery caused a crisis in statistical mechanics. If the system does not go to the standard thermal state, where does it go? Does it oscillate forever? Or does it settle into a different kind of steady state? This question led to the development of the generalized Gibbs ensemble, or GGE. In standard thermodynamics, we calculate the state of a system by maximizing entropy subject to 2 constraints: energy and particle number. This gives us a single temperature, but for an integrable gas, we have thousands of conserved charges. To describe the steady state of such a system, we must maximize entropy subject to all of them. The resulting state is the GGE. Instead of having one temperature, the system has generalized temperatures corresponding to each conserved quantity. The GGE predicts that an integrable system will relax, but not to a thermal state. It relaxes to a state that retains maximum information about the initial conditions allowed by the conservation laws. It is a memory-preserving equilibrium. This framework was verified experimentally in 2015 by Jörg Schmiedmeyer's group in Vienna. They performed interferometry on split 1D Bose gases and confirmed that the system relaxes to a state described by the GGE, not the standard thermal ensemble. The temperature of the gas was not a single number, but a complex function dependent on how they prepared the experiment. But describing the equilibrium is one thing. Describing the motion is another. For a long time, standard fluid dynamics failed to describe these gases. The Navier-Stokes equations, which describe how water flows or air moves, assume local thermal equilibrium. Since these gases do not thermalize locally, the equations broke down. This changed in 2016 with the introduction of generalized hydrodynamics, or GHD. GHD treats the integrable gas as a fluid, but a very special one. Instead of describing a fluid cell by just density and temperature, GHD describes each cell by a full distribution of rapidities. It assumes that locally, every small chunk of the fluid is in a generalized Gibbs ensemble state. This theory allows physicists to simulate the motion of the quantum Newton's cradle with unprecedented accuracy. It highlights a key difference in how these fluids move. A normal fluid flows from high density to low density, smoothing out variations through diffusion. An integrable fluid, described by GHD, behaves differently. The fast particles simply separate from the slow particles. This is called ballistic transport. The cloud shears apart in phase space rather than diffusing. GHD has effectively become the standard model for 1D quantum gases, successfully predicting phenomena like shock waves and strange heat transport properties. Now, the story gets even more interesting when we introduce imperfection. What happens if the system is almost integrable, but not quite? Benjamin Lev's group at Stanford University investigated this by building a dipolar quantum Newton's cradle. Instead of rubidium, they used dysprosium atoms. Dysprosium is highly magnetic. Unlike rubidium, which interacts only when atoms touch via contact interaction, dysprosium atoms feel each other from afar, via magnetic dipole-dipole forces. This long-range interaction breaks the strict integrability of the Lieb-Liniger model. It introduces a mechanism for the system to eventually thermalize. Lev's experiment allowed them to tune the strength of this interaction, effectively turning a knob between integrable and chaotic. They observed a new regime, called pre-thermalization. The gas would quickly settle into a GGE-like state, a plateau where it seemingly stops changing, and stay there for a very long time. Only eventually, slowly, would it drift toward true thermal equilibrium. Furthermore, they found evidence of quantum many-body scars. In classical chaos theory, a scar is a periodic orbit that remains stable even in a chaotic sea. In the quantum many-body version, these are special high-energy eigenstates that evade thermalization entirely. Even when the dysprosium gas was kicked into a chaotic regime, certain initial states would refuse to thermalize, oscillating like a zombie version of the Newton's cradle. This connects the physics of ultra-cold atoms to the same mechanisms that might protect quantum information in future quantum computers. And that brings us to the application. Why does this matter beyond the abstract beauty of it? The study of integrable gases has profound implications for quantum technology. First, quantum memory and coherence. Thermalization is the enemy of quantum coherence. It destroys the delicate superposition states needed for quantum computing. Systems that defy thermalization, like the integrable gas or many-body localized systems, suggest ways to engineer materials that naturally protect quantum information for long periods. Second, precision sensors. Atom interferometers use the wave nature of atoms to measure gravity and acceleration with incredible precision. These devices often use 1D waveguides. Understanding the non-thermal dynamics of the gas is crucial for reducing noise. If the gas does not thermalize, it does not suffer from the same thermal blurring as a normal gas, potentially allowing for sharper interference fringes and more sensitive detectors for dark matter or gravitational waves. Finally, quantum simulators. The 1D Bose gas acts as a pristine quantum simulator. By tuning the interactions, physicists can simulate the behavior of electrons in wires, magnetic chains, and even early universe cosmology. The integrable gas is a rebel in the universe of thermodynamics. It reminds us that the laws of statistical mechanics are not absolute, but emergent properties that rely on chaos and information loss. In the pristine isolation of 1D quantum traps, we can peel back this layer of chaos and observe the underlying, deterministic clockwork of the quantum wave function. From the first bouncing clouds in Weiss's Cradle to the magnetic complexity of Lev's dysprosium experiments, the journey of the integrable gas has revealed a hidden world where heat does not flow, memories do not fade, and the arrow of time can be held in suspension. As we master generalized hydrodynamics and explore the boundaries of integrability, we are not just playing with quantum toys, we are learning how to control the very flow of entropy itself. Thanks for listening to G Fun Facts Online.